This video deals with the motion of particles along geodesics in both flat and curved space to show that the velocity of these particles is a conserved quantity. Through the use of parallel transport and killing vectors, a quantity involving the energy momentum tensor can be shown to be conserved along a geodesic. So let's consider a free particle moving in Euclidean space. Now, Newton's first law tells us it will remain at rest or in a state of constant motion unless acted upon by some force. So it's going to continue at rest or continue along its existing path. So we can parameterize its path in terms of time, the time coordinate. So r of t, its position here on this two-dimensional grid, is x1 of t, x2 of t, and we can parameterize each of the x1 and the x2 in terms of the time coordinate. And so here's a suitable position vector for the path that it follows. Now, a free particle is not subject to any force, and so it moves in a straight line with constant speed or remains at rest. Okay, now geodesics in Euclidean space are straight lines. We've seen that in the previous video, if you look through that, when we used the Euler-Lagrange equations to show that was the case. The interesting thing about a straight line is that it parallel transports its own tangent vector. So the tangent to a straight line is parallel transported along that straight line. It's held constant in direction and in magnitude. And so in the case of our particle in Euclidean space, the tangent vector is the velocity of the particle, and it's a constant vector. So if we take the partial derivative of the position vector, which traced out its path, then dr dt gives us this constant 1, 1. The magnitude of this is square root 2, so the magnitude is fixed. So all along its path, it has a constant speed of square root 2 meters per second or units per second or whatever units of time are being used. du dt is 0, and we can see that as a kind of condition of parallel transport, because if this tangent vector is being held constant, then its derivative with respect to time will make it 0. So it stays constant over time. As the particle moves along the path with constant speed, no force is acting on it, it's a free particle. All right, so the condition of a parallel transport of a vector then in this Euclidean space is the partial derivative of the tangent vector, the velocity vector, with respect to time is 0. Now, we could also represent this as the scalar product of the tangent vector with respect to its derivative is 0. And the reason for that will come up shortly. In component form, we could write that as ui dui dt is 0, if we're looking just at the components. All right, reason for this will come up shortly when we go to curved space. All right, now, as I've shown in other videos, in curved space-time, particles with mass travel along a time-like world line, and the square of the magnitude of its forward velocity is given by, we use the metric to contract the tangent vector on itself. The tangent vector being the forward velocity of the particle. This is a particle with mass, and when we contract that, we get minus c squared. There's other videos in which I've done that and shown that, so please go refer to those. But all along the world line of this particle, which is also a geodesic, the forward velocity of the particle, the magnitude of the forward velocity is fixed, constant, this value here. I use a particular metric where the time component is 0 and then the spatial components are all positive. There are other metrics where that's reversed, and so you have a plus here. All right, now massless particles travel along null geodesics with the square of the magnitude of its forward velocity given by this. So for a massless particle, the magnitude is constant, it's 0 in that case. All right, so the velocity of a free particle is tangent to its world line, which is a geodesics, and just running through that calculation again, as I've done this elsewhere, but it's just worth going through again to see how we get this minus c squared. So u dot u is the vector form here in terms of the basis vectors. We're in the coordinate basis here, and we scalar product of that, bring out the basis vectors together, and the scalar parts to the right here. So this is the definition of the metric in the coordinate basis. By this, contracting, using the metric to contract, which is the lower one index, and then to sum over the remaining index, mu in this case. When we do that, we end up with this object here. Okay, a little bit of algebra. Okay, this is the spatial velocity of each of the components, and that gives you the total spatial velocity. When we work through that, we get minus c squared. So this tangent vector is a constant vector all along its world line. All along the geodesic, it has a fixed value. That's for a particle with mass. In the case of a particle without mass, this will be 0. But we approach the calculation slightly differently. All right, so parallel transport. I mentioned earlier parallel transport. So we're saying the tangent vector is parallel transported along its path. Okay, so if we have a look here, let's start with, here's a curved surface, the surface of a sphere. We have a vector at P. Okay, the vector V starts at P, red. Okay, and moves to Q and continues along its path until it returns to P at blue again. Okay, so this vector is being parallel transported across this curved surface. This is not a flat surface, and we'll see what happens when we do that. And what we do is we move this vector in very, very incremental small steps, in infinitesimally small steps, delta lambda. So if we parameterize the path in terms of lambda, then we're going to move it to lambda, from lambda to lambda plus delta lambda. Delta lambda is infinitesimally small, so we move the vector parallel to itself along this path here. All right, and we move it in very small steps, keeping the magnitude constant, keeping its direction constant. And as we move it around in flat space, when we move the entire, if this were just flat space and not the surface of a curved sphere, then the vector would come back to the same location. You can do that, you can draw that on a bit of paper, but on a curved surface, the vector always touches the curve on the surface at one point, is tangent to the curve, and the curve that's following is this one here. That's the path it's taking. Okay, but because of the intrinsic curvature of the sphere, this vector there will be a change in direction when we come to the other end. So we can hold the magnitude constant, and in infinitesimal steps we try to hold the direction constant. And as we move it, this is what happens. All right, moving it around, around, and around, moving it parallel to itself, tangent to the path it's following, touching at one point only, as a vector tangent to any path will do, touching at one point only. Eventually come back, and we find that when it's done that, it's pointing in a different direction, and that's due to the intrinsic curvature of the surface on which it's moving. So just in a little bit more detail, here's our path here in blue, parameterized in terms of the variable lambda. Okay, lambda going from say 0 to 1 or some other value, but lambda changing as we move along the path. Here's the tangent vector at lambda, and then here's the same tangent vector at lambda plus d lambda. Okay, it's just moved on by an incremental amount, infinitesimally small amount, holding it parallel to itself, keeping the magnitude constant. That is what the process of parallel transport is. Okay. All right, so in order to work out a condition for the parallel transport of a vector in curved space, let's just consider the directional derivative acting on some scalar function. So we've got some scalar function here. F is made up of f of x of lambda. You can see that I could be summed over, anything from 1 to whatever, 1 to n, depending on how you want. This scalar function is made up of these things here. Okay, then the directional derivative of f in the direction of lambda with respect to lambda, okay, will be df dx using the chain rule, dx d lambda. Now if you look at that bit, dx d lambda, that's actually just the tangent vector. Okay, and then that's the partial derivative of the function with respect to the scalar, coordinate scalar xi or x mu in this case. Okay, let's remove the scalar function, and we have a general directional derivative operator. So we have a definition for a general directional derivative operator. So the total derivative in the direction of lambda, along lambda, is dx mu d lambda, the tangent vector to the path, times ddx mu, which we can take these as basis vectors as I've shown in other videos. Now in curved space, we're required to use the covariant derivative form. So in that case, we replace the partial derivatives with the covariant derivative. And so we have this object here. So here's our operator. Next step. So the condition for parallel transport of some 4-velocity vector along a geodesic for some particle will be in component form anyway, du alpha d lambda is dx mu d lambda delta del mu, nabla mu, u alpha, or this expression here. And this will be 0 because we want to hold, remember through parallel transport, we want to hold the vector, the forward velocity, the tangent vector u alpha, we want to hold it constant. We want to hold its magnitude constant. We want to hold its direction constant and move it along some given path, wherever the particle is following. And the condition for that is that the covariant derivative of the four velocity vector is 0 in the direction of the tangent vector. Okay, so, or we can write that in vector form like this, is 0. So parallel transport vector keeps its magnitude and direction constant. Okay, that was the build up. I wanted to get at conservation of the energy momentum tensor in a particular circumstance. So let's go back to our swarm of particle that we've used over the last couple of videos. Here we are again. Okay, now in a stationary space-time, we can expect there to exist a killing vector in the time coordinate direction. So choose our killing vector as we did in the last video. And just as in the last video, the energy momentum tensor can be written in this form here, in the coordinate basis form, and one forms over here, one forms up here. We want to know if the following quantity is conserved. So the energy momentum tensor in the direction of this particular killing vector, which is in the time direction, along the time coordinate. All these other spatial parts here are 0. Here's the time coordinate 1. It's a constant vector. Okay. And this object here, as we showed in the last video, which I'm not going to do here, is actually goes from a rank 2 tensor, the energy momentum tensor, down to a vector, a rank 1 tensor. So this quantity here is just a vector. We looked at all that. It looked like the momentum density vector and so on. Here, this bit here, just point out that this can be expressed with the t down here and the t up here, and we can reverse those positions, take the t upstairs and the t down here. So same thing. Okay. All right, now just to remind ourselves that killing vectors satisfy this equation, the killing equation, and this is equal to 0, and that's a condition that all killing vectors satisfy. So our question is the divergence of this vector A that we saw before, this quantity t dot k, is that 0? Is the divergence 0? Is it a conserved quantity? Okay, so we have here, let's take the divergence. We'll do looking now at the components, and we have this over here. So we use the product rule here. So the covariant derivative, the energy momentum tensor times the killing vector plus the energy momentum tensor times the covariant derivative of the killing vector. Okay, so let's just put in our components here. We know that this energy momentum tensor can be expressed in terms of the rest mass per unit volume of the particles. So it's the particle density, the matter density, u mu ut times kt. And then over here, what we're going to do, play a little bit of a game here. I'm going to put a half out front, and I'm going to double this and put a half out front. So I've really written this twice, you can see here, and then put a half out front to halve it. So it's the same thing. Okay, but I'm going to make use of the symmetry of the energy momentum tensor to swap the indices. So keep the first term here the same as the one above, but here I'm just going to swap the indices. T and mu swap place, mu t swap place, same down here. Okay, symmetric tensor, the energy momentum tensor. And then I come down here, what I'm going to do is just take out these constants, rho 0 and ut are constants out here. Remember, ut is just c times gamma, constant out here, times the outside here is the killing vector again. But just have a look here, the key part here is that this satisfies the geodesic, parallel transport of a geodesic, right, or the geodesic equation. This parallel transport of geodesic means that this is 0. Okay, remember that was a condition for parallel transport of the forward velocity, which is a tangent to the particle's world line. So this is 0. So that whole thing drops out. And then here, this is the killing equation from above here. So this is 0. And so that we have that the divergence of this quantity, remember this vector A here, this momentum density times some constants that we found, we find that this is constant. Okay, so in the direction of a killing vector, this quantity here in the direction of the Killing vector, the energy momentum tensor is conserved, whatever that Killing vector is, but in that direction, the energy momentum tensor is conserved. So this is a conserved quantity, or we can express that as the vector A. All right, so all of which shows that the vector A is t dot k is a conserved quantity. So the inner product, the energy momentum tensor with a Killing vector, produces a second vector quantity that is conserved in the direction of the Killing vector. Or we can say that this here is a conserved quantity in the direction of the Killing vector kt. All right, that's it.